In this video, we'll discuss dielectrics. Dielectrics are an insulator that are often placed between the plates of a capacitor. The whole point of a dielectric is to increase the capacitance of the capacitor. Let's think about it for a second. If we put an insulator between our two conductors, we make it even harder for a charge to kind of jump from one plate to another, which means we're able to get more and more charge on our plates. However, there's a trade-off. We get an increased capacitance when we use a dielectric, but there's a decreased breakdown voltage or breakdown potential. Breakdown potential is the maximum potential difference that you can place between the two plates before the capacitor fails. In other words, before electrons are able to jump the gap between our two plates, which would mean it would no longer store charge. That breakdown potential or breakdown voltage is related to this dielectric strength value that you see in our chart here. And you'll see that it's in kilovolts per millimeter. So it depends on how thick your dielectric is. This table, which you can also find in your textbook, gives you a list of some dielectric constants. Those are useful in actually calculating the capacitance when we have a dielectric in our capacitor. Because if the dielectric completely fills the space between the plates, then the capacitance of your capacitor is that dielectric constant times the capacitance if there were no dielectric there. This C0 value, this is what we derived in class earlier for a parallel plate capacitor or a cylindrical capacitor or a spherical capacitor. So basically all I would do is take that equation and multiply it by this dielectric constant, which is represented by the lowercase letter kappa. Now notice that this equation only works if the dielectric completely fills the space between the plates. If it doesn't, we basically treat it as if we have two different capacitors that are connected in series or perhaps in parallel, depending on how the dielectric fills in. We'll see some examples of that in class. Just another note about dielectrics is that if we have a fixed distribution of charges, the effect of a dielectric is basically to weaken the electric field that would otherwise be present. If I'm weakening that electric field, that then means that I'm increasing how much charge I can hold, but again, with the downside of decreasing that breakdown potential. Just a couple of other things to point out about this chart that you'll see. Notice how it says for a vacuum, K equals unity. Unity is really just a fancy way of saying 1. So when we have a vacuum, my dielectric constant is 1, which is why we don't include it in our equation. You may also notice some odd things here. We said that our dielectric must be a insulator, but as you look across this list, you may see some things that we typically consider to be conductors, such as water, for example. When we're dealing with water in our everyday lives, we know it's a conductor, but that comes from many of its impurities and the fact that there are many ions in our water. The water that would be used as a dielectric in a capacitor is water in its purest form, deionized water to be specific, doesn't have any impurities, doesn't have any charged atoms, which would be your ions, and therefore it actually is a pretty good insulator. We'll see some examples of how capacitance changes when we have dielectrics, and once again also how we can deal with dielectrics that don't completely fill the space.